Okay, today we're going to be talking about forces. So my bell ringer for this lesson was there's a penny at your table. What are some ways you can move it across the table while keeping it in contact with the table the entire time? And if you think about it, there's really only a couple ways to do this. You can push it with your finger. You can pull it with your finger. And that's really about it. There aren't many other ways that you can move the penny without using those two actions, and that's kind of what we're getting at with forces. So a force is any interaction that, when unopposed, will change the motion of an object. And again, we're talking about a push or pull. Forces are a vector, meaning they have direction. So for example, if I was applying a force of 10 newtons, if it was in the positive direction, that could mean it was going to the right. And if it was negative 10 newtons, that could mean that it's going to the left. So that direction is represented with the plus or minus sign. All right, think about this scenario. You have three students. You have one that is sitting on a cart. You have one student that is pushing them, and then you have another student that is trying to stop them. So what's going to happen to the stopper when they attempt to stop the cart from moving? Well, if you've ever tried to stop a large object, like, I don't know, a car that's rolling, it's hard to stop the car or whatever object you're trying to stop without moving back slightly. And when we did this demonstration in the hallway, that's exactly what happened. So Newton's first law, and this is important, this is something you should definitely know, is an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. And again, when we talk about a force, that is a push or pull. So think about it. Right now you're probably sitting down, and you're going to stay sitting down unless something else acts on you. So if someone came over and shoved you out of your stool, that's going to change your motion. You're no longer going to be at rest. Or if you were running in a straight line, you're going to kind of keep moving forward unless something acts on you. So think about football players. When they're running straight, they're not going to change directions unless they pivot or until another player slams into them. So inertia kind of relates to the first law. Inertia is the resistance an object has to a change in its state of motion. My simple definition of inertia is objects tend to keep on doing what they're doing. And again, if you think about an object that's already moving, it's going to keep moving unless something stops it. And also, if an object's not moving, it's going to continue not moving until something acts on it. So think about this. I've got a tennis ball and I'm walking. So let me draw a little stick figure here. So I'm walking this way. If I throw a tennis ball up in the air, is it going to kind of go straight up and then come back down? Or what's going to happen? So think about that for a second. So actually what ended up happening when I did this demonstration, so I'm walking this way, and if I throw the ball up in the air, rather than coming straight up and straight down where I threw it, it kind of follows this path right here. So it continues moving in the horizontal direction because I'm already moving. So I'm moving, the ball's already moving. Even though I throw it up, the ball's still moving to, in this case, the right as it goes up and comes down. All right, Newton's second law deals with acceleration and forces. So the acceleration of an object, as produced by the net force, is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of an object. Okay, that's a really long definition, but all you really need to know is this. Force is equal to mass times acceleration. So as the force increases, the mass should also increase, or actually that's backwards. As the mass increases, the force usually increases, and also force will increase as acceleration increases. That's really what you need to know from Newton's second law. So as I said previously, the equation for force is equal to mass times acceleration. So just to remind you, when we talk about mass, we're usually talking about kilograms, and when we talk about acceleration, it's meters per second squared. So the units of force, we refer to them as newtons, but what we're really doing is we're taking the units of mass, that's the kilogram, and we're multiplying those by the units of acceleration here. So rather than saying kilograms times meters over seconds squared, we simplify that and we just say newtons. So when I did this in class, I actually had a student come up and break a board. Before doing that, I said, or I posed this question to them, considering our equation for force, what factors affect someone's ability to break the board? And if you look at the equation, we've got really two variables that can affect the force. We've got the acceleration, so this would be your hand coming into a board, so speeding up or increasing your speed, speeding up the hand that you're striking the board with. And also when we deal with mass, like the larger, let me figure out how to explain this, the more mass you're throwing at the board, the better. So obviously a bigger person would have an easier time breaking the board than a smaller person. So like I just said, these are the factors that really affect how to break a board. We've got the mass of the person breaking the board, we've got the speed of the technique, and then a lot of people, when they go to break boards, for some weird reason, right before they hit the board, they tend to slow down a little bit. So this is really just following through. On the technique, continuing to hit it with everything you've got all the way through. So the next thing I had students do was sketch and label two different diagrams of a board break. And if you think about it, if it's breaking the board, so I've got my hand, I'm not a very good artist, so here's my hand coming into the board right here. So if the board's breaking, the amount of force from my hand is going to be greater than the amount of force that the board is pushing back with. So I've got my force, F1, and then I have F2, which is the amount of force that the board is pushing back on me with. So if I'm breaking it, F1 is going to be greater than F2. So the board naturally tries to resist me when I touch it. If my force that I'm applying on the board is greater than the amount of force that the board is pushing back on me with, I'm going to go through it. So in the second scenario, when the board's not breaking, so again, here's my hand coming at the board. So again, I've got F1 and F2. So if it's not breaking, F1 is going to be less than F2. I could also say that F1 is equal to F2. So in either one of those scenarios, so like if I'm just putting my hand up against the board and I'm kind of leaning on it, the board's not going to break. I'm applying a force to the board is applying a force equal and opposite to the amount of force that I'm applying. And obviously if I'm applying less than the force of the board, it's not going to break. So really what we want to have is we want to generate a force greater than the force the board is generating on me. So we talked about these. Okay, so for the exit ticket of this class, I gave students the equation, F equals ma, and I asked them to do a math problem. We really hadn't talked about this, but honestly, it's just plug and chug. So let's take a look here. We've got a mass, and we have an acceleration. So I'm going to plug these in, so it's going to be 90 kilograms times 12 meters per second squared. And let me get my calculator out here. So we've got 90 times 12. That's going to be 1,080 newtons. And that is the force that I'm applying.